of a machine learning project to calculate and predict the power generated by a combined cycle power generation facility. Right. So in this project, we have a data set of 9,568 hourly average ambient environmental readings from a power plant, as well as the power generated. Right. The data includes variables including temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output, which is the target we're trying to predict. The temperature variable is either known as T or AT, as it's listed in the CSV file. Ambient pressure is known as AP, relative humidity RH, exhaust vacuum is V, right? So when we look at this data, we want to first understand what data we have. So we're going to load the pandas program, the Python program, and read the CSV file. We're going to take the shape of it, right? So the shape of it is like, what are the dimensions of this data? What are the rows and columns? And then we are also going to, we're going to check, null analysis, right? So we're going to do the shape, and then we're going to look at the first few rows. When we look at it, it says, okay, these look like continuous values, right? For each of these, which is what we're expecting inside the range that we were told, right? We look at null analysis, which shows that, we don't have any nulls, and then we're going to do some outlier analysis. So in outlier analysis, where we are looking at the distribution of the data, right? And to visualize the distribution of the data, we're going to use a box plot, right? From the Seaborn library. And the way the box plot works is that your median is this horizontal bar in the middle of the box, right? So half your data is above and below. And then the edges of the box are the 25th percentile and the 75th percentile. And then beyond that, we have the whiskers. And the whiskers are set to be 1.5 times the interquartile range. And the interquartile range is simply the range of the box. So you can see here that we have some outliers. But the outliers aren't too far off. Sometimes you can remove the outliers if they're too far off. But for this case, we will keep them since they're relatively close. Now we're going to do a box plot for the power generated, and you can see that there are no outliers for this. Everything is within the whiskers. Now to look at the variables, we want to decide, which variables we're going to turn into features. We're going to do some correlation analysis, right? So we're going to take a look at this, and you can see that we're going to run it against, the variables that we have: ambient temperature, exhaust volume, ambient pressure, and relative humidity. Some of these will be positively and negatively correlated. We will run this later, right? After we do this walkthrough of the code, right? When we execute this, this is some of the images that we have. And you can see this is run by this pair plot, function, right? And then we're also going to run a correlation matrix, right? The correlation matrix can use several different ways to calculate correlation, including the Pearson, Kendall, and Spearman models, and with the default model being the Pearson or standard model, right? And you can see that we are going to use, we're going to create a heat map with this information as well. We're going to create the correlation with this DF core, right, data frame correlation, and run a heat map. And then finally, we're going to run some linear regressions. So for this project, we have 4 potential features, and we will run multiple linear regression as well as linear regression just on one feature. So let's start off by running all 4 of them, and you can see that the way this works is you take a data frame, and then you say these are the columns I want to be my X, and my Y, my dependent variable, is going to be power generated. Now we're going to use this train test split function to create a training and validation sets. Right, so we're going to have a training set for X and a training set for and a validation set for X, as well as a training set for Y and a validation set for Y. X being the independent variables or the features, and Y being the dependent variable. So now we are going to run it, and then we will run the linear regression, and we will get an intercept and coefficients, and then we will calculate the errors. Right, so the errors, we like to use the root mean square error, but we are also going to calculate the mean absolute error and the mean square error. The reason we like the root mean square error is because it uses the same units as our target variable, like mean absolute error, but it also uses the it also penalizes outliers more, right? So larger variations from the model, like mean square error. So we're going to do this with 4 features, then 2 features was just the ones with the highest correlation, then 3 features, and then finally 1 feature, right? So let's run it before we cover the summary and see what data we get. So this is the output of the notebook, and you can see we had reviewed the data before, and seen that there's no nulls, and reviewed the box plots. But this is where it gets interesting for data that we didn't cover on the raw side. So you can see there's 4 different variables here. 2 of them are roughly negatively correlated, and 2 of them are roughly positively correlated. Right, so when we look at power output, we can see that ambient temperature is negative 0.95, right? So as the temperature goes up, power goes down, right? And then exhaust volume is negative 0.87. You can see it's kind of negative, similar, but it has a little bit of a curve to it, right? And then ambient pressure looks somewhat positive, and then relative humidity also somewhat positive, but also very scattered. So this is why it has the lowest correlation at 0.39. So when we run these for 4 variables, we get a root mean square error of 4.5, a mean square error of 20.8, and a mean absolute error of 3.67. Right. So when we do 2 variables, we get a higher error rates, across the board, 4.9 versus 4.5. When we do 3 features, we're going to remove relative humidity at 0.39, and you can see it's still relatively high. Like the error is closer to 2 features, like 4.89, 23 versus 24, and 3.92 versus 3.97. And then finally, we're going to try it with 1 feature. So with 1 feature, we're just going to use ambient temperature with the highest correlation, and the root mean square error is 5.38, which is higher than 4.5, right? And the way to interpret this is a root mean square error. If we look at this as like anywhere from 4.5 to 5.38, this is about 1% of the value, right, of the power generated value, right? So even though there is some variation in these models and the predictive power, it is still overall as a percentage not that different. So we can conclude that the models perform in a relative range of each other from 1 to 4 features. Right here in the summary, we say we're going to use supervised machine learning, right? Supervised machine learning because we have a target we're trying to predict, and we're going to use the root mean square error because it uses same units and penalizes outliers more. The candidates include the temperature, ambient pressure, relative humidity, and vacuum as the candidate features. And candidate models included linear regression, multiple linear regression, polynomial, or nonlinear regression, and others, such as lasso and ridge regression. But in this model, we're going to use linear and multiple linear regression, where linear is 1 variable and multiple will be 2 to 4 variables or features. We are going to split the data set, and we use the train test split function from this scikit-learn model selection library. Right, the default value is 25% of the data will be used for the test set or the validation set, which is what we used here. However, you can set this to whatever you want. And then we did the analysis, right? So as we saw with the analysis, 4 variables had the greatest predictive power, but the end result in terms of error was roughly similar to whether we use 1, 2, or 3 features in terms of percent of target value. And finally, hyperparameters were not used as there's no hyperparameters in standard linear or multiple linear regression, unlike regularization linear regression such as lasso or ridge. And finally, given that we selected root mean square error, we can indicate that this is going to be about in the 1% range, right, when we look at this. So that is the conclusion of this exercise. So if you have any questions, please post on the comments. Thank you.